Hello, everyone, and I'd like to thank you all for attending EDICON this year. My name is Zachariah Peterson. I'm going to be talking about building and using numerical and analytical models in PCB interconnect optimization. I won't get too deep into my bio at the moment, but if you would like to learn a bit more about what I do, I encourage you to download the slide deck and feel free to read over my background. So let's just jump right in. What I'm going to be talking about is optimization of PCB interconnects and optimization of transmission lines. And as soon as I bring this up, I think the natural question is, what exactly is optimization? Usually in the industry, it's a lot of marketing speak, unfortunately. But optimization is actually a serious field of mathematics, and it's used in pretty much every engineering discipline in at some level. Sometimes you don't know that it's happening, it's going on in the background. So like with auto routers are performing an optimization problem. And I think that all design engineers are very good at doing optimization subconsciously. And optimization is really about finding trade-offs in your design and finding ways to balance those trade-offs. And what I mean by that is mathematically what you're doing is you're trying to maximize or minimize some design goal. And you're trying to do that while staying within the limits of some constraints that are imposed in your design. And so we can think about transmission lines in the same way, and I'll show some examples of this and how you can actually do this. So in PCB design optimization, and within the mathematical definition of optimization problems, what we have is we have an objective function that's outlined in red, and really this is just my design goal. That's conceptually, that's all you need to think about is this is the design goal that I have set in my system, and this could be an impedance. So let's say I want to get to 50 ohms impedance. This could be an S parameter. I want to get S21 down to 0 dB. Let's say whatever else could be the heaviside condition that's actually been investigated by other researchers in the past. Could really be anything. And then I have some constraints in my design. So really, any of your design goals could have some associated constraint, and you want to try and stay within those constraints. And then you have a set of design variables. These could be signal integrity metrics, but these design variables usually end up being geometric, and this is especially true in PCBs. And so if you think about it, any of the signal integrity metrics that you might care about as you try and either maximize or minimize your way to a design goal, they end up being related to the geometry somehow, either through parasitics or directly. And so really your design variables at the end of the day are in some way geometric. And so the question in design optimization is, how do I choose my design variables so that I get to the objective function that I want, so I get to my design goal, while also staying within my constraints? And so this is kind of a simple question, but this is actually a very deep field of research, and I'll present some simple methods you can use to do it. At least I think they're simple, but there are open source packages that you can use to kind of solve these problems, and I'll get into that more later. So just as an example of where this actually applies practically in electronics and in PCB design is in newer signaling standards. So newer signaling standards that use S parameters for differential pair design, an example being 100 G base KR, another example being USB 4.0. They use these integrated S parameter metrics as your signal integrity metrics, but these really are your design goals. So you have integrated return loss defined in terms of the incoming and outgoing port S parameters, and these are defined in terms of an integral from DC all the way up to some maximum frequency. And so where you cut off that maximum frequency is really depends on the band limiting effects in your channel and in your receiver. And I'll show you, you'll see more what I mean on the next slide. Here, the input pulse could also be band limited. So it could be 0 outside of some band, and that could certainly band limit the channel. The point here is that in these integrated signal integrity metrics, you're considering what happens over a very broad bandwidth. And so this is actually the approach that I take in what I'll show here for transmission line design is you want to be able to consider the very broad bandwidth, not just one frequency. And it's kind of unfortunate because most solvers will only consider what happens at one frequency and kind of leave you to figure out the rest. So why do we need to consider a broad bandwidth? Why can't we just look at one frequency? Well, for digital design, if you look at the power spectral density of a typical bit stream, like I've shown here from Hayfich and Schlepnev, the power spectral density is actually spread out over a very broad bandwidth. Theoretically, the bandwidth goes out to infinity. Just taking 0.5 divided by the rise time, or 0.35 divided by the rise time, or whatever metric that you use to kind of quantify most of the power, it doesn't really give you the right answer. So there is some point where the bandwidth cuts off, but you still need to consider what happens to the signal throughout that entire bandwidth. So what limits the bandwidth? Well, it could be load capacitance, right? Load capacitance is basically a high pass filter back to ground. So that band limits the channel. Could be the Nyquist frequency of the receiver. Could really be anything. So however you get to that band limit, it doesn't really matter. The point is that you consider everything from DC up to that band limit. So within interconnect optimization, if you can consider the entire bandwidth, you can generate an impedance curve that actually accounts for dispersion and that accounts for roughness over broad frequency ranges. And so if you include dispersion and you include dispersion in the dielectric constant and dispersion in copper roughness, and you do this type of optimization procedure, you don't actually get a straight line at 50 ohms impedance with zero imaginary part. You actually get these kind of curves that look like this, and so they've got a little bit of wave to them. Here for the real curve, you can see it's pretty close to 50 ohms. It's not exactly 50 ohms, but it's within 1% over most of the bandwidth. So this is a pretty good design. And then there is some residual leftover imaginary part. But once you have this impedance curve, you can generate all the other important terms that you might need to know for interconnect design. So once you have the impedance, you can determine what the propagation constant is. And then once you have the propagation constant, you can get a transfer function, and you can take both of them and you can get S parameters, assuming you have a known reference impedance. So it all kind of centers around determining the impedance and determining the propagation constant first. So if you can do that, then you can do a lot of prediction and predict what you might measure in your channels. And so if you're going to do this type of prediction with numerical data or with just with tabulated dielectric constant data for your laminates, you need a model. And so, of course, the standard transmission line optimization model does have a name. It's the RLCG model or the RLGC model, depending on who you ask, referring to the resistance, inductance, capacitance, and then dissipation in a real transmission line. And so each of these terms in the transmission line impedance equation is related to, first we have a DC resistance and the skin resistance, and then we have the capacitance and the tangent and the loss tangent in our G term. And then we have the real part of the dielectric constant and this Kg term in the capacitance. This Kg term just takes account for fringing fields. And so I've included the reference here about for anyone who's interested in reading more about this model. So this is probably the best reference you'll find on it. But you also need causal models for dielectric constant and for copper roughness, and those need to translate into causal models for your electrical parameters. So the dielectric constant is easy, and I'll explain that here in a moment. Copper roughness we also need to know, and we need a causal model for it, and I'll also explain where that comes from. Now, this type of thing's actually been done in the past. This type of optimization procedure to try and predict and design transmission lines. It's just a really complex procedure that's been done in the past. So if you look at this reference at the bottom of the screen, this is the same reference as I had in the previous slide. What these guys do is, or what these guys were doing in that paper is they took measurements of impulse responses and S parameters, and then they extracted the geometric trends that determine all of the important parameters in the transmission line equation. And so basically, they have one set of measurements, they extract a model, and then they can use that extracted model to design any other transmission line that they like. So that's pretty cool, right? Problem is that it was process and material specific because the copper roughness is lumped in with the skin resistance. So in order to decouple those two, you would then have to go back and measure what the copper roughness is. And so it wasn't universally applicable without a bunch of extra work. Also, the algorithm was just way too complicated. I mean, I read through it and I was able to understand it, but I've never tried to implement it. So forget about doing that. There's got to be a better way. And so we'll look at kind of doing that in my presentation. And what I'm doing is actually going the opposite direction. So they're starting from measurements and going back to a model through extraction. I'm starting with a model, and then I'm going to do a prediction of what you might measure in a real channel. So I mentioned copper roughness earlier. To get to a causal model for copper roughness, we need to do a little bit of math and enforce a Hilbert transform on the real and imaginary parts of our copper roughness term. And to do that, you actually have to consider not just the roughness of the surface as a whole, but also the individual particulates that make up that roughness. And Schlepnev is one of the pioneers, along with Bert Simonovich, on this. And I would encourage anyone to read their paper, or this paper here, referenced at the bottom of the screen, in order to learn more about copper roughness and how it affects transmission lines. So we also need a mathematical way to quantify the effective roughness. And so the effective roughness is essentially to just increase the magnitude of your skin effect. And this is done just with a functional transformation here in the lower left portion of the screen. So essentially what this does is it also increases the dielectric constant by a proportional amount. And this is done by just comparing the case of the dielectric thickness for in a real system versus the dielectric thickness in the ideal system. And so that's done here in this top comparison. And there are a number of models that relate this copper roughness correction factor back to the geometry of the individual particles plus the arrangement of particles. And Cannonball Hurray is one of the great ones, but there are a number of others. And so you can look up all of those different models if you like in the references. More recently, though, I believe it was Schlepnev, he actually started working with tabulated data. So you don't have to use one of these models. You could actually use tabulated data here for K of omega. And you could do the same thing for your rough dielectric constant. You could do the exact same thing. So here I'm using in my method, and I'll actually use these equations, but you could use these equations, but you could also work with tabulated data. And so this is kind of where you take an analytical model and turn it into a numerical model just using your measurements. So I'm going to run through a derivation, and I'll do this kind of quickly because I know I've kind of been droning on. But to get to an analytical model that accounts for dispersion and roughness and maintains causality, normally what you do is you actually start with a model that doesn't have any of that stuff in it. So you have a model for impedance. It might be a formula. It might be something that you extracted from a field solver. However you get that model for impedance. You need to then transform that into a model that accounts for a causal dielectric constant and a causal copper roughness factor, as well as the skin effect. And to do that, we essentially, again, take a transformation. We just take a linear transformation. I'm calling it a linear transformation. It's really a functional transformation in the frequency domain from your inductance without any skin effect or anything included, and you add back in the skin effect and the DC resistance. So this term in the center of the screen on the right is the numerator in the transmission line impedance equation. And then down here for the capacitance, we apply a similar transformation that now lumps in the loss tangent. And now we have the denominator. Well, we just take numerator divided by denominator, take the square root, ta-da, we have our impedance equation. So I'll admit this is a very messy equation. Definitely not the prettiest equation, but it includes all of the important terms that you need to model transmission lines. So we have our causal copper roughness correction factor. We have our impedance, so our Z sub 0 term. We have our impedance model without any roughness or without any dispersion. And then we have our loss tangent. I'm using a negative sign next to the loss tangent because I'm a physicist. I hate when all you guys use negative signs in the dielectric constant because that's mathematically wrong. It should be a positive sign in the dielectric constant, so you should have a negative sign down here. You guys can argue about that. You guys can argue with me about that later. And then just going in and doing a similar definition with the propagation constant, you get the bottom equation in the red box here. This bottom equation, again, includes all the important terms. And so now we have everything that we need to start doing some calculations. So if I'm doing impedance optimization, I need to essentially minimize my deviation in my predicted impedance or my design impedance from some target. So just for convenience in what I'll show next, I'm going to take 50 ohms as a target impedance. And to do this, we're going to use a function from, or we're going to use a tool from functional analysis called the LP norm. And this is actually something that's normally used to compare S parameters and look at the deviation between them over a broad bandwidth. I'm using it for impedance. You could also do it with S parameters if you have a target S parameter that you want to hit. And so for P equals 2 in our LP norm in this integral, this is essentially equivalent to minimizing an RMS deviation in the complex plane. And so you can think of your target impedance as this straight line that we want to hit in the complex plane. And then I have some contour that kind of wraps around this. And as I tune the geometry of the interconnect, this blue curve kind of eventually collapses down to this red dashed line. And so that's my goal in my optimization problem. So I'm just going to run through a quick example of how this works. I'm going to do an example with an 8-layer stack up. Just for simplicity, I'm calling it, equal dielectric layers, standard thickness. I picked out some values for roughness. I'm going to go with a 25 centimeter line. Let's just say for a moment we have 1 picofarad load capacitance or whatever. What's really important here is the constraint that I've defined. And so the constraint, not normally defined as a ratio, but here the actual important value in this method is this ratio. And if you actually looked at analytical equations for impedance in other references, then you're probably aware that this is actually the important metric that you need to optimize. So it's this width divided by height. And then we have our parameters for our dielectric constant. So here I'm using a 2-pole model. The standard model is a wideband Debye model. Again, this is just a wideband Debye model, but summed up to 2 terms, because those are the only 2 terms that really matter in our bandwidth. And so the bandwidth, you'll see in the next section, is taken out to, I believe, 10 gigahertz. So the optimization algorithm that's used here is called differential evolution. And there are like hundreds of different types of differential evolution algorithms. This is basically a random search algorithm. You can tune this so that it's a directed search algorithm. And there's a lot of there's a lot of research into these types of algorithms for solving different types of engineering problems. So here's our results, and what I've done is I've provided some comparisons here. So our rough line is with copper roughness and skin effect and dispersion included, and our results say that we should have a 7 mil wide line. And you can see here on the right the impedance curve, and it actually gets very nicely close to 50 ohms throughout this pretty broad bandwidth. So that's pretty great. There's a little bit of imaginary part left over. That's okay. Just for comparison, I did a line that has no dispersion or skin effect. It's a little bit wider, and if you actually take that value and put it into the rough line, you can actually compare the two, and you can see how they deviate from each other. And they actually don't deviate very much. What's actually interesting is to look at also what a commercial method of moments field solver says. And the commercial field solver says that you get down to 50 ohms once you have 7.614 mils. And so this is a very popular field solver that I won't name the company that makes it here in this presentation, but I'm sure some people in the audience have used it. And so in our smooth dispersionless line that's used in the commercial method of moments field solver, because we don't have any roughness or dispersion, this is our value that we're using for dielectric constant. And again, this is just taken at 1 gigahertz. And so this kind of, as we look at the next slide, you'll kind of see the folly of just taking these calculations at just one frequency as compared to taking the calculation over a very broad bandwidth as I've done. And so when we look at the S parameters, you can see the commercial solver has the worst value. You can see obviously the smooth line, as you would expect, has the best return loss and the best insertion loss. In the insertion loss curve, it almost totally overlaps with the commercial solver result, and so I've omitted it just for clarity. And in the taking the smooth width and putting it into the rough model gives you almost the same insertion loss. In fact, you can just barely see it. High frequencies is where they start to diverge, but you can clearly see that they're actually quite different in terms of return loss. Now, once you have all of this, you can then do your tests for causality, and you can actually calculate the impulse response. So the impulse response that I've shown here is using the input impulse that's defined in IEEE 802.3 standards that's used for testing Ethernet channels. But you could use any other impulse you like. And so once you have these other terms, you can calculate the transfer function. You then use a procedure in the reference below to enforce causality in that transfer function. And then you can do the standard convolution with the transfer function and the input pulse, and you can determine the response. And in our rough line, we actually get pretty nice results. The smooth line on this scale looks like it should give very nice results. It actually doesn't once you zoom in, and so I've shown here the standard view zoomed into the channel response in the upper right, and you can see it actually dips down below and has kind of a steep, it dips below zero and has kind of a steep rise on the left side of the curve. So going further, these types of analytical or mixed numerical models should be modified to calculate things like differential impedance, take account of fiber weave effects, which is actually a stochastic problem, but it's one that is very near and dear to my heart. And you do, at that point, you are working purely with numerical models if you really want to be accurate. And so this is where new techniques like machine learning are becoming very important in order to account for all of this. one of the big challenges there is that they have to deal with multiple objectives, or they have to take account of multiple aspects of a process or material that aren't generalizable to any other channel. And so there's a lot of research going on in this. Typically, you have so many different objectives that you have to balance. It can be difficult to balance it all. There's a numerical model here that looks at some of this, and I invite the audience to look at this particular paper because it's actually quite interesting, even though it is a very old paper. So I'd like to thank everybody for listening, and I welcome your questions. Here's all my list of references.